Last time we have seen how to obtain the solution of a non-homogeneous linear differential equation of nth order with constant coefficient if q of x is equal to e to the power ax. And for that purpose, we have seen the two theorems. The theorem 1, if f of a not equal to 0, then 1 upon f of d operate on e to the power ax is equal to e to the power ax upon f of a. You have seen this is the theorem first. Now in the second part, if f of a is 0, then what happens? If f of a is 0, this means that d minus a is a factor of f of d. Suppose this factor repeated r times, means we take f of d is equal to d minus a to the power r into phi of d, where phi of a is not equal to 0. And if we operate this on q of x, we want to see. Now means we have seen the theorem second. If f of d is equal to d minus a to the power r into phi of d, where phi of a is not equal to 0, then 1 upon f of d operate on e to the power ax is equal to 1 upon d minus a to the power r into phi of d operate on e to the power ax, and this is equal to x to the power r e to the power ax upon r factorial into phi of a. We have seen these two theorems, also the proof of these two theorems, and we have seen the example based on this topic. Now we want to go to the next. If u of x is of the type x to the power m, where m is a positive integer, means m is a natural number, then in that case, we have when we operate 1 upon f of d on x to the power m, in this case, we expand 1 upon f of d in ascending powers of d and operate the various operators of d on x to the power m. We know that m is a positive integer. Therefore, m plus mth derivative of x to the power m is constant, and m plus 1 and the highest order derivative of x to the power m is to be 0. It vanishes, means is to be 0. Therefore, when we expanding this 1 upon f of d in ascending powers of d, in that expansion, we consider the term up to only d to the power m. We neglect the remaining terms since m plus 1th order derivative and highest order derivatives to be 0. Now, when we are operating this 1 upon f of d on x to the power m, it is customary for us to write this f of d into the linear factors, and then we write this in the partial fraction. And for that purpose, we want to use the following theorems or following standard expansions. We have used already we have seen these expansions in FIBSC class. 1 upon 1 minus alpha is equal to 1 plus alpha square plus alpha cube plus dash dash dash. Next, 1 upon 1 plus alpha is equal to 1 minus alpha plus alpha square minus alpha cube plus dash dash dash. Next, 1 upon in the bracket 1 minus alpha bracket square. It is 1 plus 2 alpha plus 3 alpha square plus 4 alpha cube plus dash dash dash. and the next expansion is 1 in the bracket 1 plus alpha bracket square. This is equal to 1 minus 2 alpha plus 3 alpha square minus 4 alpha cube plus dash dash dash. We want to use this standard expansions when we want to solve the examples, or we want to find the particular integral of the non-homogeneous differential equation if q of x is having the term of the type x to the power m. Now we want to see the example based on this. Solve the equation in the bracket d cube plus 3d square plus 2d bracket complete of y is equal to x square plus 2x. Now to find solve this equation means we want to find the general solution of this non-homogeneous differential equation, and we have seen that the general solution of this non-homogeneous differential equation contains two parts, the complementary function and particular integral. To find the complementary function is very. For that purpose, we consider the associated homogeneous differential equation of this non-homogeneous differential equation, and we find its general solution, and the general solution of this associated homogeneous differential equation is to be the complementary function of this non-homogeneous differential equation. And we have seen this in the previous topic, how to obtain this general solution of the homogeneous differential equation. And to find the particular integral, we have seen that yp is equal to 1 upon f of d operate on q of x. We use that technique. Now to find first the complementary function, first suppose this is the given differential equation. From this we consider the associated homogeneous differential equation, and the associated homogeneous differential equation is what? In the bracket d cube plus 3d square plus 2d bracket complete of y is equal to 0. From this we consider the auxiliary equation is m cube plus 3m square plus 2m is equal to 0. Now from this we have to factorize this, take m common, then we get here m cube, here the plus 3m square m cube plus 3m square plus 2m is equal to 0. From this take m square, m to be common. In the second bracket we get m square plus 3m plus 2 is equal to 0, and the factors of this is m plus 1, m plus 2. Here also you take the small m. Now this is m plus 1, m plus 2 is equal to 0. Therefore, m is equal to 0 minus 1 minus 2. Roots of the auxiliary equations are to be real and distinct. Therefore, complementary function yc is equal to c1 e to the power 0x plus c2 e to the power minus 1 into x plus c3 e to the power minus 2 into x. Means we get this yc. Simplifying this, we get this is yc is equal to c1 plus c2 e to the power minus x plus c3 e to the power minus 2x. Now we want to find the particular integral. Therefore, we consider yp is equal to 1 upon f of d operate on q of x. Here f of d is d plus 1, d plus 2, and q of x is x square plus 2x. Therefore, we operate this 1 upon d, 1 plus d, 2 plus d on x square plus 2x. Now we operate this one by one. This is one method, or other method we write this in the partial fraction form using partial fraction. If we use here the partial fraction, We know that how to obtain the partial fraction. We get this 1 upon d into 1 plus d into 2 plus d. This can be written as 1 upon 2d minus 1 upon d plus 1 plus 1 upon 2d plus 2 operate on x square plus 2x. Now we simplify this bracket and we operate one by one. 1 upon 2d operate on x square plus 2x minus 1 upon d plus 1 operate on x square plus 2x plus 1 upon 2d plus 2 operate on x square plus 2x. Now here operating 1 upon d, we have seen this is the integration only. Now in the second operating 1 upon d plus 1, now to use our standard expansion, for that purpose we write the denominator as to be 1 plus something. Now here we rearrange this, we write this 1 upon d plus 1 as to be 1 plus d, and then we use the formula 1 upon 1 plus alpha for the expansion. Again here to operate 1 upon 2 d plus 2, 1 upon 2 is constant. Now to operate d plus 2 on this, we have to write this 1 plus something. Now to write this 1 plus something, for that purpose, we have to take the lowest degree term to be outside. Remember this. For that purpose, we take the lowest degree term to be outside. Here 2d to the power 0. 2 is constant, means this is the lowest degree term. Therefore, from this d plus 2, we take 2 common. Do not take d common. Here we have to take 2 common. Therefore, we get this is equal to 1 upon 2, and 1 upon d means integration of x square plus 2x dx minus sign as it is, and the expansion of 1 upon 1 plus d is 1 minus d plus d cube. I avoid these terms and higher order terms or higher powers, since here the terms in the x square plus 2x, its power is 2 only, means third order derivative of this comes to be 0. The same way for the next 1 upon 2 as it is, and from d plus 2 we take the 11th degree term common, means if we take 2 outside of this bracket, this becomes 1 upon 4, and in the bracket 1 plus d upon 2. If we take 2 common, we get d upon 2 plus 1. We write it as to be 1 plus d upon 2 operate on x square plus 2x. Again, for operating this on, we use the expansion 1 upon 1 plus alpha. Just here we have used that. The same we have to use this here. Alpha is d upon 2. Now, if we see, we simplify this 1/2 as it is. Integration of this is x cube upon 3. Integration of this is x square upon 2. These 2 gets cancelled. We get x square minus 1 into x square plus 2 minus the derivative of this is 2x plus 2 plus second derivative of this means derivative of this, it is to be 2. We drop the remaining term. Third derivative is 0 and so on. Plus 1 upon 4. Expansion of this is 1 minus d upon 2 plus d upon 2 square, means d square upon 4. We avoid the third degree term. Operate this on x square plus 2x. Now we simplify this. We get this. We first simplify this bracket x cube upon 6 plus x square upon 2 minus x square. Here plus 2x minus 2x becomes 0. Minus 2 plus 2, it becomes 0. Right? We rearrange this in this term. Right? We have only minus x square. Now the next 1 upon 4 into bracket 1 into this means x square plus 2x minus 1 half derivative of this 2x plus 2 plus 1 upon 4 second derivative is 2. And again simplify this. After simplification, we get yp is equal to x cube upon 6 minus x square upon 4 plus x square upon 4 minus 1 upon 8. This is the particular integral. And then we write the general solution. is to be y is equal to yc plus yp. We obtained yc previously and then we add this yp. This is the general solution of the given differential equation. Now we see the second example. Solve this equation. D cube plus d of y is equal to x to the power 4 plus 2x plus 1. Again, for this purpose, first we find the complementary function, and we know that how to obtain the complementary function. From this, consider the associated homogeneous differential equation in the bracket d cube plus 8 bracket complete of y is equal to 0. From that, consider the auxiliary equation m cube plus 8 is equal to 0. We know the factors of this. Use the result x cube plus a cube. Using that, here m plus 2 and in another bracket m square minus 2m plus 4 is equal to 0. If we find the roots of this, then we get m is equal to minus 2 and 1 plus or minus root 3i. Now one root is real and non-repeated and another two roots are complex conjugate of each other and non-repeated. Now we know that how to write the solution corresponding to the roots. Therefore we get yc complementary function is c1 e to the power minus 2x plus e to the power x into bracket c2 cos root 3x plus c3 sin root 3x. This is our complementary function. Now to find the particular integral, we consider yp is equal to 1 upon f of d operate on q of x. Means yp is equal to 1 upon d cube plus 8 operate on x to the power 4 plus 2x plus 1. Again, to take the expansion of this 1 upon d cube plus 8 in ascending powers of d. For that purpose, we take the lowest degree terms to be outside. Do not write its factors in the linear form and quadratic irreducible, then it becomes lengthy. Here we directly take the lowest degree terms to be outside. In the denominator, the lowest degree term is 8. We take 8 outside and then we write this as to be 1 upon 1 plus d cube upon 8 operate on x to the power 4 plus 2x plus 1. And we know that how to take the expansion of 1 upon 1 plus alpha. Use that result. Here alpha is d cube upon 8. Means its expansion is 1 upon 8. 1 minus alpha plus alpha square minus alpha cube dash dash dash. Using that, here 1 minus d cube upon 8 plus d cube upon 8 is square. D cube upon 8 its square is d to the power 6 upon 64 minus d cube upon 8 its cube. Means it comes to be d to the power 9 and so on divided by 64 into 8. We get this in this way. Means higher order derivative is not necessary. Here the highest power of this x is 4x to the power 4. Therefore, the derivative of highest order is to be 0. Fifth order, sixth order derivatives are to be 0. We avoid that terms and directly we simplify this. This is equal to 1 upon 8. 1 into this as it is minus 1 upon 8. Third derivative of this. Now see here, what is the first derivative? 4x cube plus 2. First derivative is 4x cube plus 2. Second derivative is 12x square. And third derivative is 24x. I have written directly here, third derivative. Now simplifying this, we get yp is equal to this. And then from this, complementary function and particular integral, we write the general solution as to be addition of this complementary function and particular integral. Therefore, this is the general solution. This is the general solution of given non-homogeneous differential equation. Again, we consider the third example now. Solve the equation d square plus 3d plus 2 of y is equal to 1 plus 3x plus x square. As usual, find the complementary function. For that purpose, consider the associated homogeneous differential equation. From this, consider the auxiliary equation, find its roots, find the factors of this, m plus 1, m plus 2. Therefore, m is equal to minus 1, minus 2. Roots are real and distinct. Therefore, complementary function is c1 e to the power minus x plus c2 e to the power minus 2x. Now we want to find the particular integral. Yp is equal to 1 upon f of d operate on q of x. Here f of d is d square plus 3d plus 2 and q of x is x square plus 3x plus 1. Therefore, we take this, operate this on q of x. Now again here you may write in the partial fractions, means we write the linear factors and then partial fractions and then operate one by one. This is the one method. Another method, directly here take the lowest degree term to be outside from this and then operate that. Here 2 is the lowest degree term. If we take it outside, then we get 1 upon 2 into 1 upon 1 plus d square plus 3d upon 2 operate on 1 plus 3x plus x square. Again use our formula for expansion of 1 upon 1 plus alpha. This is 1 half 1 minus d square plus 3d upon 2 plus d square plus 3d upon 2 bracket square. We avoid the third degree term since the third order derivative of this q of x comes to be 0. Now only we simplify these two terms. 1 half 1 minus d square upon 2 minus 3d upon 2. Now here if we take the first term d to the power 4, fourth derivative is 0. We neglect that term. The multiplication of these two terms and its double, it comes to be 3d cube and its double is 6d cube, means third derivative is to be 0. We avoid this and last term is 9d square upon 4. 9d square upon 4. Only we consider the last term of this bracket. Right? Now we simplify this. We get this. Simplify first this bracket 1 minus 3d upon 2. Combining these two, we get 7 upon 4d square. Operate on this. Now operate this one by one. 1 half 1 into this 1 plus 3x plus x square minus 3 upon 2. First derivative of this is 3 plus 2x plus. Here there is, we have to simplify this as to be 7 upon 4. Here is the correction. Instead of 2, here there is the 7 upon 4. We get this 7 upon 4 and the second derivative of this, means first derivative of this is 2. Simplify this, we get this 1 minus 9 upon 2 and whatever may be plus 7 upon 2. Please check this calculation. There may be a, this is to be changes due to here we have to choose this as to be 4. If we simplify this, this is to be 3x and this minus 3x gets cancelled. We get this 1 half x square and this 1 minus this 9 upon 2 and plus 7 upon 2 means minus 1 half. If we take 1 minus 9 upon 2 plus 7 upon 2. means it becomes -1, and this +1 gets cancelled, means this term is 0. Please correct it. Means we get yp is equal to this. Therefore, the general solution is y is equal to yc plus yp, and this is equal to c1 e to the power minus x plus c2 e to the power minus 2x plus 1 upon 2 x square. This complete this example. I think on this topic, this much example is to be sufficient. We have seen the 3 examples on this topic. Now, for practice, you may take these examples. You solve these examples. It, these are the examples on both the topics. Okay, we stop our today's lecture.